Nearly 60 years after Star Trek introduced audiences to the concept of warp speed, a once fictional dream is edging closer to genuine science. For generations, traveling faster than light was relegated to the realm of fantasy, a convenient plot device to bridge the unimaginable distances between stars. But the line between fiction and physics is beginning to blur in the most astonishing way. Recent studies now suggest that a warp drive might not actually break the fundamental laws of physics. For a century, Einstein's theory of general relativity has been the bedrock of cosmology, establishing the speed of light as the ultimate cosmic speed limit. Nothing with mass can reach it, let alone exceed it. Yet, new theoretical frameworks are showing us a clever way around this universal rule. Even more remarkable, new theoretical models eliminate the need for exotic negative energy, long considered the biggest, most insurmountable obstacle to making such a drive possible. This isn't a minor tweak, it's a paradigm shift that has reignited serious scientific inquiry into a field once dismissed as speculative fiction. The challenge has shifted from if to how. In this video, we'll explore the latest research that has made this possible, delve into its mind-bending scientific foundations, and examine what it all means for the future of interstellar travel. Warp travel began as pure storytelling, a necessary invention for a new kind of television. In 1966, Star Trek creator Gene Roddenberry faced a narrative problem: the sheer scale of the galaxy. To tell stories of weekly exploration, he needed a believable way for the crew of the Starship Enterprise to cross galaxies without resorting to magic or teleportation. His solution was elegant. They would travel by bending space-time itself. The idea, rooted in the language of Einstein's relativity, resonated deeply with both fans and scientists, planting the seed for decades of speculation and inspiring generations to look at the stars and wonder, what if? In 1994, that what if was given a mathematical backbone when physicist Miguel Alcubierre turned fiction into theory. He proposed a model showing how space-time could be compressed in front of a spacecraft and expanded behind it. This would create a warp bubble that could move faster than light, without the ship itself ever breaking Einstein's local speed limit. Think of it like a surfer on an ocean wave. The surfer isn't moving through the water, but is carried along the water. Similarly, space inside the bubble would remain perfectly normal and calm, but the bubble itself could travel superluminally by riding a wave of warped space-time. The catch? It was a very big one. Alcubierre's equations demanded negative energy density. This is a form of exotic matter with bizarre properties, like repelling gravity instead of attracting it. Not only has it never been observed in nature, but the amount required was staggering, quantities equivalent to the mass of the Sun. For decades, the Alcubierre drive remained an elegant mathematical curiosity, a fascinating thought experiment confined to the pages of physics journals, seemingly destined to stay there forever. Then, in 2021, a groundbreaking paper by physicists Alexei Bobrik and Gianni Martea proposed a revised version, a physical warp drive. Their model brilliantly replaced the need for impossible negative energy with positive, physically realizable energy and matter. By reconceptualizing the bubble's structure, they showed that a shell of conventional mass could, in principle, create a contained warp field. Though it couldn't yet exceed light speed, it proved that a warp bubble could exist within the known laws of physics. This was the critical step. For the first time, warp theory became a legitimate scientific framework, not just a sci-fi fantasy. It moved from the realm of the impossible to the realm of the extraordinarily difficult. This breakthrough changed everything, providing a new lens through which to view interstellar travel. The Bobrik-Martea model clarified the core concept. A spacecraft wouldn't need to outrun light. Instead, space-time itself would do the moving. Inside the bubble, the ship would remain effectively stationary while the universe shifted around it. This ingenious concept neatly avoids time paradoxes and remains fully consistent with general relativity, solving another major theoretical headache of older models. However, the energy requirement, while no longer exotic, is still immense. To create even a sub-light speed bubble, the model calls for an energy density roughly equivalent to the mass of several planets like Jupiter. Yet that's a finite, calculable number, not a physical impossibility. It's an engineering problem, not a fundamental barrier. And researchers believe that refining the geometry of the bubble, making it flatter, longer, or altering the thickness of its walls, could drastically reduce the energy demand over time, potentially bringing it within the realm of a future civilization's capabilities. Another fascinating development emerged in 2024, shifting the focus from creating warp bubbles to detecting them. Scientists proposed that the formation or collapse of warp bubbles could emit unique and powerful gravitational wave patterns. This suggests that our existing gravitational wave observatories, or their future successors, could one day detect such signals. This would not only confirm the physics, but could also reveal the presence of other civilizations using advanced warp technology, transforming warp physics into a powerful new tool for the search for extraterrestrial intelligence. The field remains entirely theoretical, of course, but it's now grounded in real equations and peer-reviewed physics, not just hopeful speculation. Scientists worldwide are exploring new ways to generate, stabilize, and detect these space-time distortions, turning once fictional ideas into a serious and collaborative field of research. To be clear, a functional warp drive isn't almost here, but thanks to these recent breakthroughs, it's also no longer considered fundamentally impossible. And even if humanity never achieves faster-than-light travel, the study of warp physics itself already holds immense value for science. It forces scientists to probe the absolute limits of Einstein's relativity and the nature of space-time itself. Much like how early rocketry research advanced materials, science, and gravitational wave research opened a new window on the cosmos. The pursuit of a grand challenge often yields unexpected, revolutionary discoveries along the way. In fact, a subluminal, or slower-than-light, warp bubble could still completely revolutionize space travel within our own solar system. By isolating a spacecraft from the harsh environment outside, it could protect the crew and sensitive equipment from extreme G-forces, micrometeoroids, and harmful cosmic radiation, making long-duration missions to the outer solar system far safer and more practical. The implications extend far beyond propulsion, opening up entirely new fields of astronomy. Instead of searching only for alien radio signals, scientists could soon begin to scan the cosmos for gravitational footprints, the subtle, telltale ripples in spacetime caused by the artificial manipulation of gravity for propulsion or other massive engineering projects. Of course, monumental challenges remain on the path from theory to reality. Humanity currently lacks any conceivable means to produce or control such colossal energy levels. The energy needed is orders of magnitude beyond our entire global output. Furthermore, the physics of stabilizing a warp bubble, or preventing its catastrophic collapse into a black hole, is a problem far beyond our current engineering capabilities. Yet unlike before, these are now seen as technological and engineering challenges, not violations of fundamental physics. The problem has moved from the physicist's blackboard to the engineer's drawing board. Future research will focus on three key areas: continuing to refine the theoretical models to lower the immense energy demands, developing laboratory-scale analogues using fluids or metamaterials to simulate warp phenomena, and searching the skies for natural space-time distortions that could offer real-world insight. Scientific progress always moves from imagination to theory, and then from theory to technology. It's a long and arduous path, but one humanity has walked many times before. Warp drive is now firmly in that crucial middle phase. No longer just an idea, but a theoretical concept grounded in real, testable physics. Whether it ever flies among the stars or not, one thing is now clear. Warp drive is no longer just science fiction. It's a genuine scientific pursuit, one that is already reshaping our understanding of space-time, gravity, and the ultimate boundaries of what is possible.